here to talk about the Internet of Things and the effect it has on the Internet, on cloud computing and on data analytics. If we're in the wrong room, now would be a good time to leave. So the Internet of Things. Well, as you probably already know, it's all about devices being directly connected to the Internet one way or another. We're all familiar with the ideas of things like fitness tracking, health monitoring, stuff sitting around the home. So, for example, monitoring temperatures, potentially controlling your home remotely. These are all familiar ideas. This is all part of the Internet of Things, otherwise also known as the Internet of Everything, and some cynics would call it the Internet of Tat. And they call it that because a lot of the press and a lot of the journalism, a lot of the articles you read about are all about things like fitness applications, home applications, what have you. These are really sort of consumer type things. But actually the Internet of Things is much bigger than that and extends beyond people and their homes and their vehicles and into towns and cities and commerce and industrial. And in fact there's a huge number of applications across the board where Internet of Things has some relevance or some use. And if you were to think that actually the Internet of Things is all hype, there's a huge number of companies involved in developing stuff for the Internet of Things, and we have several layers here. So at the top we have platforms and infrastructure. So there's a number of companies building infrastructures for you to build applications on top. So for example, they'll handle all the networking, collection of data and billing and analytics for you, so you can just build applications on top. There are companies building vertical applications to exploit the Internet of Things, all the way from fitness and lifestyle through to managing homes, etc., etc. So a lot of the stuff on the left-hand side is all the consumer side. On the right-hand side we have more industrial Internet of Things applications. There's a lot going on. And of course everybody talks about the Internet of Things being something in the future, but actually it already exists. So we are here, and there's already some devices sitting around us. Forgive the internet is a bit slow today. So this is a map of the Internet of Things that's sitting around us here at the watershed. So we are up here somewhere, and we can see there's a bunch of devices sitting around us. We've got different colour coding. If we look here, for example, we see that these ones here, these are all experimental devices. I think something's going on in the watershed, I'm not quite sure what. There's obviously a centre of activity. These purple ones are transport based, and then the blue one is environmental, and the yellow one is energy. This is a Thingful, which is like a Internet of Things search engine. I'm not sure how up to date it is, but it gives you an idea of potentially what's happening at the moment. And as we zoom out, we see more and more devices, and you'll notice that as we zoom out to world level, there's actually quite a lot of transport devices out there being tracked at the moment. So that's where we sit currently today. And actually that's just a small part of what's about to happen. The number of devices that are being connected to the Internet is going to absolutely rocket. And to give you an idea of where it is in the scale of things, in terms of the number of sites you have on the Internet, we are probably talking in the order of about 1 billion. The number of people connected to the Internet is probably about 5 billion. And the number of devices by 2020, some predict to be 50 billion. Even when you look at conservative estimates, so for example Gartner, fairly conservative about this, they claim 20 to 25 billion. But that's still a huge number compared to the number of people. And this is literally another revolution in terms of where we are in terms of computing. So many years ago, back in the 1970s, for example, everything was inside the enterprise. Then we moved into business to business, then people to people with social media and what have you. We've had machine to machine, and some people think machine to machine is Internet of Things, but it isn't really. Internet of Things is another layer on top of that. And that's something we're looking forward to now. So one aspect of the Internet of Things is connected cars. And when I think of connected cars, I've generally thought, well, okay, well, there's probably a couple of sensors in a car. That's pretty much it, really. But actually, there's going to be a whole wealth of them. Hopefully, most of them aren't talking to the internet all the time, and hopefully, for example, the fire detection sensor isn't continuously telling us about a fire. But there is a lot of data which is potentially being produced by a connected car. And people in the know, for example, tell me that Ford Fusion energy car, I've no idea what that is, but it exists apparently, and it's producing 25 gigabytes an hour as of today. Ford are experimenting with cars which go 10 times that, so we're looking at 250 gigabytes. The Google self-driving cars, they generate about the order of 3.5 terabytes an hour. Some estimates I've seen even potentially predict cars generating 1 terabyte a second. Now, I think that's probably a little bit on the high side, and I doubt all of that's actually going to be pushed into the internet. But there will be a lot of data produced, particularly with driverless cars having to communicate and coordinate with each other. There will be a lot of cars around, so cars with IoT applications will be looking into the many hundreds of millions by the 2030. So there's a lot of data being produced. And data velocity, the numbers are quite staggering. So if you look at telecoms, you might have a network which has got 10,000 cells in it, and those cells can be producing data for management purposes, the order of about 1 million messages a second. Even an aircraft liner, a turbine can have 3,000 sensors, each producing measurements at 100 per second. And an oil rig, again, tens of thousands of sensors, all running at 100 hertz. In fact, from my own experience, I generally come from a sort of telecoms background, and some of the applications I deal with today deal with probes which are connected directly into the network infrastructure, and producing 1 million messages per second from a single probe is actually quite normal. It's not ridiculously fast. So the data velocity from some of these sensors is enormous. And the amount of data we're talking about is just going to be absolutely huge. So I've kind of only recently just got used to the yottabyte, but apparently now we're going to have the brontobyte, which takes us to the next level. And when you think about it, most of the big data applications you look at today even struggle to deal with a few terabytes. So we are talking about orders of magnitude in terms of a paradigm shift. I've generally talked about the Internet of Things covering consumer applications and industrial applications, and this is actually two different worlds. Consumer applications are on the right here, and it's all the stuff you're used to, but actually it's the industrial applications which provide a much bigger domain in terms of applications, and also in terms of their demands. So, for example, if we divide the two types of Internet of Things into consumer and industrial, and then we see no matter what aspect we look at in terms of network requirements, the industrial Internet of Things is much more demanding. So everything from data rates through to the data volumes you've got to handle, latency requirements, even time requirements, and fault tolerance, even down to security as well. Every single aspect, the industrial Internet of Things is a lot more demanding than the consumer Internet of Things. So the consumer Internet of Things, we can think about things like fitness devices, and they're just occasionally sending stuff into the internet. And you can imagine, actually, if we were connected to a cloud data center, that would probably work. No big problem. If we talk about the number of people and the number of sensors they have, no big deal. But when we come to the industrial Internet of Things, talking to a cloud doesn't really work anymore in the way we think of a cloud at the moment, because it isn't reliable enough, it can't handle bandwidth, and it's got too much latency. In fact, if you think about a device which is talking to the internet today, or even in the future, it potentially is going to have multiple hops to get into a conventional cloud center. And it may be traversing all sorts of types of networking protocols. So it might start off with Wi-Fi, it might hop across several nodes using Zigbee, and it might actually end up into some sort of wireless or mobile network. And you can imagine with all these hops, then you have more issues with connectivity, with reliability, latency, et cetera, et cetera. What's interesting, actually, in addition to these well-known technologies here, and some new ones like the low-powered wide area networks, there's 5G. So 3GPP, by the way, that's the standards body that deals with all the 3G and 4G level communications you see in mobile networks today. Slightly strange term given it covers 4G. But 5G is the new boy on the block. When I first heard about 5G, like most people I suppose, I assumed, okay, well it's going to be a faster network, but do I really want to be able to download a movie onto my mobile in a second? Probably not. Am I that interested? Not really. But 5G actually aims to do some fairly amazing and fundamental things. They're talking about 1,000 times the data volume, plus also 1,000 times the number of connected objects. So it isn't just about phones anymore. We're now talking about devices. And 1,000 times the velocity, 100 times the velocity. Married to that with the fact that it's talking about 1/10 of the energy consumption, much better latency, much easier and less expensive to manage. And really, if we go back to the previous slide, 5G is aimed to straddle the networks. So we're used to mobile networks being very expensive, being probably slightly unreliable, being high cost, and Wi-Fi being the opposite side of that. And 5G aims to straddle across those two and actually give you, part of the standards actually is to use multiple technologies, including Wi-Fi, and it's designed to give you the best of all worlds in terms of cost and availability. So given the problems we have with the Internet of Things and what we know about the cloud at the moment, can we really marry the two? Probably not, because the cloud is nothing like a sort of ubiquitous, omnipotent cloud of vapor. It actually is a number of distinct data centers, all of which are huge, but probably don't sit anywhere near the device that's actually needing to talk to it. And as we know of the Internet today, it does have pretty much limited bandwidth. It obviously has latency issues that we know about, and connectivity isn't great, to be honest. It's not that reliable in terms of having to guaranteeing to talk to a cloud data center. If we're talking about an industrial process, which is devices generating data, and we need to manage, need to process to actually look at that data and control the industrial process itself, we can't rely on talking to a remote cloud data center to do that. And this is where something called fog computing or edge computing comes in. So we have our our set of devices at the bottom. We have a cloud data center sitting at the top. And rather than having devices talk directly to the cloud, we're now introducing a layer of computing called fog or edge computing. So it sits a lot closer to the data. And this solves a number of problems. So obviously things like if we have computing closer to the devices, then we can solve things like latency and bandwidth issues, because they're not having to ship all of that data all the way to the central cloud. And actually, if we think about trying to connect all these endpoints to the cloud, then the only way we could do that would be to assume we've got infinite bandwidth and we've got no latency, if that model's going to work. And clearly, that isn't going to work. So we do have to put something in the middle. And in that model, we have to assume there's going to be some sort of limited bandwidth, some kind of latency and delay, and intermittent connectivity. At every level of this, we've got to assume those realities for the Internet of Things to effectively work.
What was called fog?
Well, it's just clouds sit high up in the sky, and then the fog is closer to the ground.
Still.
Yes. It's actually, fog is a Cisco term. So they've probably trademarked it, and I probably should put a trademark around it. But
You already owe them some money.
I do, yeah. Another term for it is edge computing. And the Internet of Things World Forum has a protocol model for the Internet of Things. So we have edge devices, we have network connectivity, we have processing, and then we have storage. Then we have data abstraction, and then all the business processes and applications and whatever sit above that. And of course, at the storage level, which is where a lot of the analytics goes on, below it we have processes requiring it and using it on an event-based model. There's very much data in motion that's going into storage, being processed, and everything's happening in real time. And above it is much more query-based, data is more at rest, and it's less real time. But this storage model and this processing model sits further down in the network, closer to the devices. And what we think of as cloud computing now and cloud data centers sits much higher up. So really, as we said, a new approach is needed. So now we've come from analytics 1.0, which was get answers in days and hours. Essentially, it's all about structured data. We're currently at analytics 2.0, which is more about unstructured data, generally speaking. We get answers in hours, minutes, and seconds. When we get to the Internet of Things, we're getting into analytics 3.0, which is much more about response times in seconds and milliseconds, depending on which side of the network you're on. And interestingly, the data that you get in the Internet of Things is now going to become massive, and it is actually pretty structured data. The stuff's coming out in JSON probably, or variations of JSON, but actually fundamentally this is structured data, it's not unstructured. So we've talked about moving the computing closer to the devices. We're going to have to analyze this data, we'll store it and analyze it. Presumably, we have enough databases around, and we have enough frameworks, and we have enough interested parties to be able to solve this problem as it stands. Because there's all this activity going on around data analytics. But actually, no. If you think of a conventional big data analytic platform, it consists of a cluster of nodes all held together with very high bandwidth interconnect. Now, something like Hadoop, as we've got an example here. It's got 1,000 odd nodes, all connected through something amazing like 10 gig or InfiniBand even. And something like Hadoop, for example, pretty much has an unstructured schemaless data model, not necessarily appropriate to the Internet of Things type data. Even if you talk about Hadoop, it relies heavily on things like partitioning to get good responses. There's a lot of design work that goes into Hadoop to get it to perform. It isn't a case of just bolt your nodes together, stick your data in, away you go. It'll work, but it might take a long time to come back with a response. And also, these things are designed for the data center. It's where bandwidth is good. Not designed for sitting out in a hostile environment closer to the edge of the network. And these things all rely on boundary security. security of Hadoop isn't great. It just hopes the fact that any intruders will be stopped at the network and data won't leak out through the network. Hadoop itself has nothing to protect your data in it. And whether we're talking about Hadoop or whether we're talking about MongoDB or any of the other types of databases that we talk about today, generally they have a similar sort of architecture. When things like Cassandra and what have you are different in that they are more designed to be more distributed, but essentially they tend to be more operational as opposed to analytical. And in fact, rather than a data center, we are probably talking about something looking like this when it sits at the edge. So this is a Cisco mini computer, the UCS Mini. It can store up to 3 terabytes of storage. Probably got about 8 cores in it. It's running at 2 gig, 64 gig of memory. And that's probably the resources you're going to have to store a couple of terabytes of data at the edge of the network. And you're going to have to do all sorts of processing and analytics on that little box. Nothing like the Hadoop running in a data center. Interestingly, 5G, back to that, talked about speeds and the number of devices connected to it. But actually 5G is actually a lot more than just speed and latency and devices. It changes the fundamental way you think of a network. And 5G is introducing the idea of combining communications with processing. So having devices talk to each other and processing data is all part of the 5G network. It isn't just talking about communications from A to B. And so 5G is actually a game changer in terms of a new networking standard. And it is designed from scratch with the Internet of Things in mind. So, for example, I think there's in South Korea we've got the World Cup coming, I think, in 2018, and 5G is going to be running there at that event. But I think all of that is going to be about download speeds, nothing more. It's going to be an early version of 5G, and it's just going to be about speed. But actually 5G has a number of phases to it, and in the long term it's much more than that. So if we're talking about analytics in a fog model, where we have thousands of database nodes sitting out in the network, how is that database going to behave? Well, in reality, it's got to be eventually consistent because we need it to be highly available and it needs to tolerate partitions. So within the CAP theorem, those are the two I need. So I've got to basically sacrifice consistency and go for eventual consistency, which is probably fair enough if I've got the majority of my data arriving from distributed locations. Also, something you've got to bear in mind is version compatibility. If I've got thousands, hundreds of thousands of database nodes sitting out in the world, at no point in time will they ever be all running at the same version. It's going to be a constant cycle of upgrading software all around these various databases. So they've all got to be able to interoperate in a friendly manner. So those are some of the fundamental behaviours of a Internet of Things database. When it comes to controlling it, again, we've got tens to hundreds of thousands of nodes sitting out there. Each one is a database in their own right. And we need to be able to manage all of those. Clearly, I can't really manage it if I just think of it as a huge mass of systems. I've got to actually have some sort of arbitrary hierarchical viewing planes to view them and to manage them. And I need to be able to create logical viewpoints within that massive databases to be able to understand what's going on. And clearly, I'm going to have all sorts of performance and fault management instruments to be able to cope with those. And I need some sort of central way of managing my data. So I can't afford, for example, to go onto each of these nodes and say, I need to get rid of data that goes beyond a certain date. that has to happen automatically, and that policy has to be controlled from a central point. And similarly, when it comes to data planes, so moving away from managing it, looking at how I query it, I need to be able to think of all this data in local, regional, and in a global sense. And I need to be able to plug myself into this network at any one point and say, when I view this, for example, this massive data as just in a sense of this is all data from California, or it's all just from the UK, or wherever, or it's just from San Francisco, and I need to be able to do that. And I need to be able to unify all that massive data within that particular region. And to effectively do that, I need to be able to orchestrate all these databases to give me those answers. And there's going to be a level of peer-to-peer orchestration between them for doing things like pipelining results. So if I think of it as a hierarchy, I have a huge set of devices sitting at the bottom. Those are arranged into regions. Maybe I'm looking at the global level. So in order to form a query, I've got to reach out to all my regions, and my region has got to reach out to all my devices. They've got to pull data back up, the results back up, and those regions have got to pipeline those results and process them and send them back to the central point, as a simple example. And it's got to be a lot more reliable. It's got to be autonomous. These things are going to have to run out in a lights-out environment. So one key aspect here is these databases sitting out in the wild have to be pretty agile and responsive to any query you throw at it. I can't afford, if I've got hundreds of thousands of databases sitting out there, I can't afford to actually go through some sort of design process and change my partitioning method or my indexing schema in order to deal with a new set of queries. I just need to issue a query. Those systems have got to come up with a response in good time. Plus, they've got to be able to discover, so it's got to be design-free performance. So I can't afford the time to actually design my database schemas or my database structures in order to give me good performance. The databases just have to deliver autonomously. They're also going to have to discover data autonomously as well. So data is going to be shoved at them, and they're going to have to take it on board as it comes. They've got to be hardware efficient. Think of the UCS Micro earlier. This isn't going to be some huge scale-out model to deal with terabytes of data. I mean, the crazy thing today is if I use something like Hadoop to analyze 10 terabytes of data, I'm probably going to have some cluster which has got 100 terabytes of storage in it to do it. That doesn't work in this kind of scenario. If I've got 10 terabytes of data, I'm going to need something which pretty much stores 10 terabytes of data. They've got to be obviously highly resilient and available in this distributed model. There's going to be some sort of automated data replication between them. So data is arriving at one node, and it's got to spread that data out amongst its neighbours in order to give me resilience and good availability. And again, I can't manage that on a node-to-node basis. I've just got to give out some general policy which says you will send your data to your nearest neighbours or whatever. And data lifecycle management has to be automated as well. You can't go around dropping data or deleting data on a regular basis. You've got to say, okay, well, each node is going to keep X days, X weeks, X months worth of data, and then after that it just drops it. And that just happens. And it's a policy I set centrally, and it happens at every single node. Security is an interesting one. Security is pretty bad these days. And you can imagine in the Internet of Things, with all these devices producing their own data, it gets even worse. We not only have to think about the privacy of the data, but we also have to think about safety of processes. So we have computer systems sitting at the edge, receiving data, monitoring it, and sending control instructions back to other devices or actuators to do things. We clearly don't want people hacking into those and changing the way processes work. There's, should we say, health and safety implications connected with that. And so not only do we have safety to worry about, we have privacy, we also have a very increased attack surface. So we've got hundreds of thousands of devices, or billions of devices. So the opportunity to hack into that network becomes that much greater. And they're all sitting in a very hostile environment, not sitting in data centers like we have now. I mean, we have stuff sitting in data centers, and yet they still get hacked. Can you imagine what it's going to be like when everything's sitting out in small buildings at the edge of the network? So some of the solutions that are coming on board, when it comes to one problem you have is device identity and authentication. How do you know that the device you're talking to is actually the device you think it is? And that problem, actually, the proposed solution for that is actually going to borrow from Bitcoin, and there's some proposal around using blockchains and cryptographic networks in order to deal with authentication of many, many billions of devices. Clearly, we need fairly firm data-centric access control. So what processes, what users can see which data, and that's got to be at a pretty granular level. And finally, pervasive community-centric encryption. So I can't rely on the network to secure my data. Each database has to probably encrypt virtually everything that it holds within it, so that even if someone comes through the network, they get into the database, they have no access to that data unless they have the right keys to get to it. And this community-centric aspect means that actually different communities can see different sets of data within the same database, and even the DBA has no access to the data. They can see the schema maybe, and they can understand what's going on in the database and manage it if they need to, but they have no access to the data underneath. So Gartner's take on this. I guess you're all familiar with the hype cycle. Interestingly, the Internet of Things is right at the top at the moment, so we're at the peak of expectations right now. So things are just going to get worse. We're going to drop down into the trough of disillusionment fairly shortly. So is everything lost? Actually, no, because if you look at the color coding, we expect to reach our sort of a plateau of productivity in 5 to 10 years' time. So by 2020, we'll have gone through all the hype, we've gone through all the despondency, and we'll actually have something which is finally there. And I'll leave you with one philosophical question, which is what we've been talking about. Are we really just augmenting the cloud with edge computing? Or are we talking about moving the cloud into the edge, extending it right to the edge? I think this latter model probably is more accurate. So we now need to start thinking about the cloud as something which is much bigger than just a few data centers. Thank you.